Hi, my name is Kurtis Splatter.
I'm Don Manuelito.
I'm Jasmine Mahaney,
Jessica Dalby.
and this is our team.
Woo!
Hey, my name is Kurtis Splatter. I'm in Chemistry 130 at Chandler Gilbert Community College. I'm working E6 of some Pearson textbook. This is for a group project. So yeah, the problem basically states that we're given 70.0 milliliters of nitrogen gas and 45 milliliters of oxygen gas, and what we want to calculate is the volume produced of N2O3. So the process of going about doing that is going to just be 4 simple steps. One is to balance the equation. 2 is going to be to calculate the limiting reactant produced from the nitrogen gas, so N2 production. And then the third step is going to be the amount that the oxygen produces. And the fourth step will be stating basically which one has the lesser amount, and that will be our final answer. So from there, let's go ahead and start with number 1. We're given these two things. We don't need to worry about the actual volume yet. We just need to worry about the amount in moles. So we have to write down the equation, then balance it. So we can write that as N2 plus some amount of O2 creates N2O3, and some amount of that. And this is all in gas. So yeah, we look at this and we can see that there is already N2 on both sides of this. So whatever number is applied to the right-hand side is automatically going to be applied to the N2 on the left-hand side, so we can go ahead and keep that in mind. In order to balance the oxygen part of the left-hand side, we see that we have 3 oxygen here and 2 oxygen here. The smallest number that those can multiply to are 6. So if we wanted to turn 2 into 6, we'd multiply by 3. So we do that. And then with O3, in order to get that to be 6, we multiply that by 2. As I said, since there's N2 on both sides, N2 is not connected to anything over here and it doesn't affect anything else, this automatically becomes 2 nitrogen gas. So that's step 1, we're good there. Then we have to state the amount of gas that could be possibly produced for the N2O3 from nitrogen and oxygen gas. Nitrogen and oxygen gas are in their natural form N2 and O2, so that's why they're that way. So yeah, let's go ahead and do the next step. So number 2, let's use a different marker to keep organized. So we're given 70 milliliters, 70.0 milliliters of N2. Let's not use that marker actually. So 70.0 milliliters of N2, and then we have to refer back to the proportions that we had listed in the balanced equation earlier. So we have 2 moles of N2 and 2 moles of N2O3. So we want to keep everything balanced, so we're going to divide this by moles of N2 to keep it consistent. Moles of N2, and we had two of those, and we're going to divide this by that. So 2 mole of N2, N2O3. That's a 1-to-1 proportion. So our final answer for step 2 would be 70. We're actually going to write it down a little further. So for step 2, we're saying that it could be 70 milliliters of N2O3 gas produced. So that's from step 2. Now we have to calculate from step 3. We use the same process as last time, so we were given 45 milliliters of oxygen gas. And then we multiply that by 2 over 3, still keeping the units similar and making sure that the stuff crosses out. So yeah, 2 moles of N2O3 over 3 moles of oxygen gas. And then that becomes our second option from step 3, which would be 30.0 milliliters of N2O3 gas. Then, as we had stated in step 4, we basically just take the lesser number, which is 30.0 milliliters of N2O3 gas. So our final production of mixing together oxygen gas and nitrogen gas from these amounts, 70.0 and 45.0, gives us 30.0 milliliters of N2O3. And that's the answer.
Hi, I'm Jasmine Mahaney. I'm taking Chemistry 130 right now. Today I'll be doing a mass-to-mass problem and showing you how to work through it to get a gram of magnesium sulfate. So we'll start off, here's a equation, and we're going to have to actually balance it out first. So we can tell here, there's one magnesium here and here, and one sulfite here and here. The only thing that's not matching is this equation and this equation. So what we're going to do is go ahead and put a 2 in front of the H2O. So we'll write out the problem. And then here's the 2. Alright, the next step we're going to do is go ahead and take what's the given mass here, which is 1 gram, and we're going to figure out 1 gram of magnesium hydroxide and the mass of magnesium sulfate at the end. So first we'll put the 1 magnesium hydroxide. Okay. And so from this, we know that we need to move on from grams to grams. So 1 gram of magnesium hydroxide, so we need to translate that to moles. So then we know that after adding up, okay, we're going to add up the molar mass of magnesium hydroxide, and we know that that is 58.383. Okay, so we're going to enter that here. And that is just 1 mole. Okay, so then from here we can go ahead and cancel out this and this gram. Okay, so then now we know that we need to get another mole here in order to get to the magnesium sulfate. So, So again, at this point we notice that from our balanced equation that there's only 1 magnesium hydroxide, and then there's only 1 magnesium sulfite. So that's basically putting a 1 and a 1 in front of here. Okay, so then it's 1 mole. Oh, I'm going to run out of room. Okay, so then from here we can go ahead and erase the moles. And so now we have 1 mole of magnesium sulfate, so now we need to figure out what the molecular mass of magnesium sulfite is, and that is 120 38 grams magnesium. I'm sorry. Alright, so then we put the 1 mole of magnesium sulfate down here, and that is 120.38 grams of magnesium sulfate. Okay, so from there, we can go ahead and get rid of these moles, and what we're left with is the mass of magnesium sulfate after it reacts with 1 gram of magnesium hydroxide. Alright, so now we take our calculators out and you go ahead and do the math, which would be 120. Okay, so then from here when you do the division, it's 2.06 magnesium sulfate, okay? Okay, and now we're going to go ahead and do the second equation, which would be to take 6.605 grams of sulfuric acid and find out what the mass is of magnesium sulfate. So So again, we're going to go through the same steps of getting rid of the grams of sulfuric acid. So we know that sulfuric acid, after adding up the molecular mass, is 98.09 grams. Okay, so we're going to go ahead and insert that here. Right, and from there we know that's 1 mole. Of sulfuric acid, okay? So now we know that we can go ahead and get rid of this. Then our next step is to convert mole to mole. Again, which is because there's only 1 mole of sulfuric acid and only 1 mole of magnesium sulfate. 1 mole. And then 1 mole. And from this point we can go ahead and get rid of this. So now we just need to figure out 1 mole of magnesium sulfate, and the molecular mass of magnesium sulfate after adding everything up is 120.38. Get this out of the way. Okay, so then now go ahead and get rid of this and that. And then what you're left with is the magnesium sulfate. So we go ahead and do the math with that, and that it ends up being and so basically what we can learn from this is that of the 2 masses from the first equation and this equation, that if 1 gram of magnesium hydroxide reacts with 0.605 grams of sulfuric acid, the mass of the magnesium sulfate produced is 0.742 grams of magnesium sulfate. Okay, and that's it. Thank you.
My name is Jessica, and I'm going to be teaching you about limiting reactants. So in our original problem, it tells us that we need to have we need to find the mass of the water produced when 1 gram of aluminum hydroxide is reacted with 3 grams of sulfuric acid. We have our original equation that was given to us as part of the problem. I have gone ahead and balanced it ahead of time, which you should be able to do yourself. we also need to find the molecular interpretation of the coefficients from the equation. And basically all that does is it puts in the mole representation for every single one. I have added in a 1 for my AlSO4-3 for the sake of clarity. I've also pre-configured all of the molar masses for the 3 substances that I will be using in order to make this whole thing a little bit faster. And so what we'll start off doing is figuring out all of our unit factors that we'll be using. We're going to be relating first our aluminum hydroxide, the AlOH3, with the water that we are looking to find. And we will also be relating the H2SO4 with the water again. So our unit factors are going to be 2 moles of AlOH3 to the 6 moles of water. And you're going to want to reduce that. So it's actually going to be 1 to 3. And then we're going to flip that, so I'll just write them reduced. 1 mole AlOH3, forgot that guy, over 3 moles of water. And then we're also going to have the reverse of that then. So 3 moles of the water and the 1 mole of AlOH3. And then we're going to need to determine which unit factor needs to be used. So we'll start the problem off with our given of the 1 gram of our aluminum hydroxide. And we're going to want to take our grams, turn it into moles. So we're going to use the molar mass formula. Our molar mass of aluminum hydroxide is the 78.01 grams. We'll put that on the bottom so that it cancels out. And that's going to be 1 mole of aluminum hydroxide. So these bad boys cancel, leaving us to divide 1 gram by 78.01 grams to equal 1, 2, 8. It's a really long number, so figure that one out. Of aluminum hydroxide. So now we are going to want to take our moles of aluminum hydroxide to get moles of water. So we'll take our resulting factor and just make sure that you did not round that number between calculations, because you will get your answer wrong. And to determine your unit factor used here, you refer back to your 3 to 1, because we're going to put the aluminum hydroxide on the bottom to cancel that out, and water on the top, because we would like to remain with moles of water. So, moles cancels of aluminum hydroxide, leaving us with 0.00384560608 moles of water. And then finally we're going to take our moles of water and transfer into grams of water, which is ultimately what we're trying to find. So rewrite this. And we're going to use the molecular mass ratio one more time, but this time it is going to be the molecular mass of water. We're canceling out moles, so we'll put our 1 mole on the bottom with our molecular mass of water being 18.02 grams. Cancel, cancel, multiply across. ultimately giving us 0.693 grams of water that was produced when our 1 gram of aluminum hydroxide was reacted with the sulfuric acid. That was a cut screen. Everything's gone. However, this is our answer from the previous part telling us that the water produced in grams from the 1 gram of aluminum hydroxide was the 0.693 grams. So that's there to refer back to later. Now what we're going to be doing is figuring out the water produced from 3 grams of sulfuric acid. So we'll find our unit factors of the ratio of sulfuric acid, which is 3 moles of the sulfuric acid H2SO4 over 6 moles of water. And again, you're going to want to reduce this bad boy. So we have 1 mole of the sulfuric acid to 2 moles of water. And we will also have its reverse of the 2 moles of water to 1 mole of sulfuric acid. So we'll take our given of the 3 grams of H2SO4 and we are going to apply the molar mass ratio to it so that we can get from grams to moles of sulfuric acid. So 1 mole of H2SO4 is equal to its molar mass being 98.09 grams. And cross out your unwanted and divide across. 3 grams divided by the 98.09 gives us 0.03058, bunch of numbers. And you make sure to write them all out because you do not round between calculations. And that is going to give us our moles of H2SO4. Now from our moles of H2SO4 we want to get to moles of water. So we will start a new line. And use our unit factor that we found earlier. We are canceling out moles of H2SO4, so that goes on the bottom. And our 2 moles of water on top. Get rid of your unwanteds, multiply across, and that leaves you with 0.0611, bunch of numbers that we are not rounding in between. And that is our moles of water. Now we want to transfer those moles of water into grams of water for this one as well. So last line, promise. Whoa. And for this we are going to use our molar mass again. Of water this time is 18.02 grams per mole. Whoa. We'll just put that in there now. So our 1 mole of water is 18.02 grams. Get rid of our moles because we don't want those bad boys. And multiply it across to give us the total of 1.102 grams of water. Now, to go back to the point of this problem, we are trying to figure out which of our 2, either aluminum hydroxide or the sulfuric acid, that is going to limit the amount of water that we are producing. So, our original answer from the 1 gram of aluminum hydroxide gives us the lesser value in this reaction. So the limiting factor, the limiting reactant, is going to be the aluminum hydroxide. So, final answer, the 1 gram of aluminum hydroxide is the limiting reactant.
Hello, I'm Dawn Manuelito and doing a problem for Chem 130, and my problem is number 59. And with this problem, we're going to see if 40 grams of molten iron 2 oxide reacts with 10 grams of magnesium, what is going to be the mass of the iron that's produced out of this formula here? Prior to this formula, I've calculated our molar mass for iron oxide, which is going to be 71.85 grams per mole. I also calculated the molar mass for magnesium, which is 24.31 grams per mole. And we're going to use these calculations in this equation using a molar mass equation, and it's going to be a mass to mass, mass to ratio, and back to mass to get our moles and ratios with the final outcome. With this, we're going to start with our given, which is we're going to have 40 grams for the iron, as stated up here, and then we're going to have 10 grams, because these are what's going to be the reactants. So these are given. Again, we're going to use given again, and with 10 grams here. Now with that, we're going to transfer it over. This is also known as a single replacement. Okay, so where we're going to start right now is we're going to start with the iron, because that's what we're going to use our given. We're going to start with our mass to mass ratio, going from grams to moles, and then we're going to calculate the moles to ratio. Considering this is a single replacement, we only have, it's a 1-to-1 ratio. So then we're going to go back from that to a mass to mass ratio, getting our grams back to moles. So we're going to start with what is given, which is 40 grams. Of our iron. Mass to mass ratio. And it's we're looking to cancel out our grams to balance this out. Moles for every iron. It's going to be. Here is where we're going to use our molar mass equation. So we've already calculated it out. And that's going to be 71.85 grams per mole. And I do things as we go, so this is grams. Here, your grams cancel out, per iron. So those cancel out. So we're going to proceed to the mole ratio, and that's going to be, again, it's a 1-to-1 ratio. And we're looking for iron, so we're going to solve for iron right now, and it's going to be 1 mole of iron to 1 mole of FeO. Okay, so here you can see the coincidence, so we're going to cancel those out. They're the same, mole iron. And then we're going to use our calculations of what we got for iron. We look at our periodic table, it's going to be 55.85. And we're going to go from moles back to grams. So we're at 55.85 grams of iron per 1 mole of iron, which equals out, which when you do the calculations, it's going to come out to 31.1 gram of iron. And this is going to be, we're looking for the 40 grams of iron, how it reacts with 10 grams of magnesium. So this is what it reacts with, and for the iron first, that's the first one. The second, this is our first part, we have to calculate. The second part will be, we have to start with magnesium, and when we start with magnesium, what we have here is 10, what is given is the 10.0 grams of magnesium, okay, and then we're going to use the same mass to mole ratio, and then we're going to go for mole ratio, and then we're going to go back to the mass to mole ratio again, or conversions. So we're at 10 grams of magnesium, and we're going to start our conversion chart again. So it's going to go 1 mole of magnesium, and we're going to add in our calculations of molar mass of magnesium, and that's 24.31 grams of magnesium. So if you can see here, the grams of magnesiums are going to cancel out. We're going to take the ratio, which is a 1 mole of magnesium of iron, got these mixed up, to 1 mole of magnesium. And with that, we're going to use our calculations of iron, because we're solving for iron here, and here we're solving for iron as well, which is going to give us our conclusion for the reactant agent. So here again we have 55.85 grams of iron per 1 mole of iron. We're going to cancel out. We're going to do our calculations here, and with that calculation is going to come 23.0 grams of iron. So with this being said, we go back to our question, and what is the mass of iron produced when you compare the two of 40 grams or 10 grams? The limiting reactant found is 23.0 grams of iron will be the mass of iron produced. There you go.